Hi, I'm Kai-Hsiang Chou. I will be presenting our paper, Bots Can Snoop, uncovering and mitigating privacy risks of bots in group chats. This work was done with Yiming Lin, Ian Wang, Jonathan Weiping Li, Tiffany Hyun-Jin Kim, and Hsu-Chun Hsiao. Most of us have used a group messenger before. In many messaging apps, we can create groups, and in some of them, we can also add chatbots. For example, in the image, there's a chatbot that creates a Google Meet link whenever someone gives a comment. As of 2021, there were about 430,000 active chatbots on Discord. These chatbots were used in an estimated 30% of all groups. Telegram also hosted over 10 million chatbots. However, chatbots can be overprivileged. First, they may read messages that have nothing to do with their purpose. In fact, some chatbots can access every message in the group. Let's use a phishing detection chatbot as an example. The chatbot may have access to all messages, even those that don't contain URLs. In our case study, we look at a Q&A bot on Discord. We found that it was reading many more messages than it needed to do its job. To fix this, we suggest limiting a chatbot's access to messages that are relevant to what it's supposed to do. We call this selective message access. Second, chatbots often learn who sent a message, even when that information isn't necessary for their task. With access to sender identities, a chatbot could track a user across different groups. In our case study of a Telegram conversation dataset, we found that 3.6% of users encountered the same bots in multiple groups. To address this, we aim to hide the sender's identity from the chatbot. We call this sender anonymity. Ideally, a secure messaging platform should provide both selective message access and sender anonymity without breaking end-to-end encryption. To explore whether this is achieved in practice, we surveyed chatbot implementations on popular messenger platforms. We set up chatbots on these platforms and examined the messages they received, along with any metadata attached to those messages. We also tested whether the message contents were protected by end-to-end encryption. The results are summarized in the table. We can see a clear tension between achieving two properties and supporting end-to-end encryption. On WhatsApp, Viber, and Signal, user bots, which are automated user accounts, preserve end-to-end encryption as expected. However, they do not provide selective message access or sender anonymity. Line does support end-to-end encryption for group chats, but when a chatbot is added to the group, encryption is disabled. And even then, selective message access and sender anonymity are still not supported. Telegram and Discord do support selective message access, and Slack also supports sender anonymity. However, none of these platforms offer end-to-end encryption. A notable exception is Keybase. Keybase supports both end-to-end encryption and selective message access, making it the only platform in our study to limit chatbot information access without compromising end-to-end encryption. However, due to its protocol design, sender anonymity is still not supported. So, why is it so difficult to achieve these features while keeping end-to-end encryption? The main reason is that end-to-end encryption requires a group key agreement scheme to decide the encryption key. Ideally, this scheme should also rotate the group keys. However, existing solutions face three main problems. For selective message access, we need to make sure that even if a chatbot has missed some messages, it can still decrypt the messages intended for it. If the message key keeps rotating, the chatbot might miss some key updates. On the other hand, if the key does not rotate, then the chatbot may still be able to decrypt messages that were not intended for it. The confidentiality of a message should not depend on whether the ciphertext is hidden from the chatbot. For sender anonymity, we need to update keys without revealing who made the update. However, most common key agreement protocols leak who is updating the key and therefore do not satisfy standard anonymity. To address these challenges, we propose SnoopGuard, a secure messaging protocol built on top of existing tree-based continuous group key agreement schemes, or the CGK schemes. SnoopGuard supports both of the key properties. Moreover, our protocol is designed to be easy to integrate into existing group messaging protocols, such as the sender keys protocol and the MLS. The core technical contribution of SnoopGuard is the compressed multi-root tree, or CMRT for short. CMRT is a novel group key agreement structure that extends tree-based CGKA. When there are only regular users in the group, the CMRT looks exactly like the underlying CGKA. The users are represented as leaves of the tree, and the groups share a common group key denoted as G. Let's suppose we want to add a chatbot to the group. When the chatbot 1 is added, we do not place it into the CGK tree as a regular user. Instead, we create a small tree with two leaves. One leaf is the copy of the root of the existing tree, and the other leaf is the chatbot. These two leaves derive a shared root called S1 using the standard CGK process. For regular users, the entire tree structure is feasible, including G, S1, and C1. However, for the chatbot, the view is limited. It can only see the small tree at the top, and the only information it has about the user's CGK tree is the copied root node G. Because the chatbot only sees the root node, the user's key updates are anonymized, and therefore the CMRT achieves sender anonymity. When the second chatbot C2 is added to the group, we follow the same process. As a result, there are now two small trees attached to the user's main tree, one for each chatbot. With this design, each chatbot has its own state and does not interfere with the others. This solves the problem of the key agreement when we want to allow selective message access. Next, let's look at how users can send messages to chatbots. When the user wants to share a message with chatbot 1, the user first updates the CGK tree, producing a new group root G'. This update then propagates upward into the small tree for C1, and which results in the new roots for that small tree. The user can then encrypt the message using S1', which is a key shared only between the users and the chatbot 1. Note that the field for chatbot 2 remains completely unchanged. It is unaware of both the message and the key update. If a user also wants to share a message with chatbot 2, the process is the same. The user first updates the CGK tree, producing a new group key G'. Because the user still holds a copy of previous group key G, the one from the last time C2 received an update, the user can propagate the new key update to C2. Then the user can use the new key S2' to encrypt the message. And once again, throughout the entire process, chatbot 1 remains completely unaware of both the message and the key update. If chatbot 1 wants to send a message, it updates its small tree and derives a new key S1'. It then uses this key to encrypt the message. Again, because we have multiple roots, the tree of chatbot 2 remains unchanged. Furthermore, users can handle the key update from chatbot 1 without requiring chatbot 1 to know the user's subtree. We evaluated the performance of SnoopGuard both theoretically and empirically. From a theoretical perspective, for a group with n users and m chatbots, adding a chatbot requires all n plus m operations, while sending a message requires all log n plus m operations. For comparison, we also include the complexities of the MLS and the sender keys protocol. MLS requires O m plus m for adding a chatbot and O log n plus m for sending and receiving messages. The sender keys protocol also requires O m plus m for adding a chatbot, but only O1 for sending and receiving messages. As we can see, when sending a message, the complexity of SnoopGuard increases linearly with the number of chatbots. This is higher than the complexity of the MLS and the sender keys protocol. However, this is usually not a problem because most schools do not have a lot of chatbots. We also implemented SnoopGuards integrated with MLS to measure its performance in practice. We measured the total time it takes for all clients to add a chatbot and to send a message. As shown in the figure, both adding a chatbot and sending a message introduce only minimal overhead to the protocol. However, SnoopGuard has some limitations. I would like to highlight a specific limitation of SnoopGuard, its dependence on the trigger function. The effectiveness of the system depends on how accurately the trigger function can decide whether a message is relevant or not. If the trigger function is poorly designed or deliberately decrypted in a malicious way, it could end up labeling every message as relevant. In that case, a chatbot would effectively gain unrestricted access, bypassing the protections SnoopGuard is meant to provide. However, we believe that addressing this issue may be beyond the scope of the messaging protocol itself. One way to mitigate this risk is through a vetting process. This could be done manually or with automated tools to ensure that trigger functions behave as intended and cannot be abused. Finally, I would like to point out some future research directions. Developing privacy-preserving chatbots for group messaging platforms is not just a technical challenge, it's also a human-centered one. While our work with SnoopGuard lays a foundation by addressing two key privacy properties at the protocol level, there are still broader areas that need exploration. The first area is usability. Privacy features only matter if users understand and use them. This means designing interfaces that make chatbot presence clear, explain what permissions a chatbot has, and make it easy for a user to grant or restrict access. The second area is permission models. Current approaches are fairly static, but group dynamics and user needs change over time. Future work could explore adaptive frameworks, potentially using natural language processing to help users decide, for example, if a chatbot should read a message or if it should be sent anonymously. Finally, we need to better understand user perceptions. Most research on user perceptions look at one-on-one chatbot interactions, but group settings are largely unexplored. Gaining insight into child's privacy concerns and engagement will be critical for designing effective systems. To wrap things up, let me summarize what we've shown in this work. First, we demonstrated that chatbots can actually learn from irrelevant messages and even identify who the sender is. These raise privacy concerns. Second, we pointed out a key challenge: how to limit what a chatbot can access without breaking the guarantees of end-to-end encryption. That's not a straightforward question. Then we introduced our solution, SnoopGuard. It's a secure group messaging protocol that allows selective message access and supports sender anonymity, all while still preserving end-to-end encryption. In short, SnoopGuard provides a new way to balance functionality with privacy in encrypted group chats. Thank you for listening. For more details, please refer to our paper.